Here's our composition function that we formed. This is f composed with g, which we found by wherever there was an x in the function f, we replaced it with the entire expression of g of x. And that, when we simplified the expression, created the expression 6x squared plus 2. So let's suppose we want to evaluate this new composed function at x being, let's say, -1. Well, as with any function, we simply take this value that we've now put in place of x, and we put it in place of x in the function expression. So the square of -1 is 1. 6 times 1 is 6. 6 plus 2 is 8. So f composed with g evaluated at -1 gives us a value of 8. If we wanted to find the value of the composition function at, let's say, 3, wherever there's x in the composed function's expression, we would replace that with 3. 3 squared is 9. 9 times 6 is 54. 54 plus 2 gives us 56. So the value at 3 of f composed with g is 56. And we would actually be creating ordered pairs, just as we have done before. This would be for the composition function. You'd have the ordered pair -1, 8. You'd have the ordered pair 3, 56. And we could graph this function, which was the composition of those previous two functions. We could graph that function the same way we graph any function. Find ordered pairs, then be able to sketch the graph. So finding the value of a composition of two functions is relatively straightforward when we have the function expression. Well, what's going on here? What's going on in terms of things we talk about as far as domain and range? Let me show you graphically what's happening here. Here we have our function f composed with g. And let's say this is the domain of that function. This is the range of that function. Well, we now know if we put -1 in for the x value, that it mapped to 8 in the range, as it mapped through the composition function f composed with g. When we let x be -1, which is a value that's a legitimate value in the range. In fact, this is just a straightforward quadratic function, so its domain would be the set of all real numbers. So that's a legitimate value in the domain of our composition function. -1, when we square -1, we get 1. 1 times 6 is 6. 6 plus 2 is 8. But watch how that relates to the two original functions that we had. -1 is a legitimate domain value for the function g of x, isn't it? G of x is a quadratic function. Its domain would be all real numbers. So if we think about this value also being part of the domain of the function g, when we evaluate that function at -1, -1 squared is 1. 1 times 3 is 3. 3 plus 1 is 4. -1 would map to 4 under the g function. But 4 is a legitimate domain value. 4 is a legitimate domain value for the function f. And if we evaluate the function f at 4, 2 times 4 is 8. That maps to the value 8. That was the range value for the composition function. So one way to find the value of a composed function when you don't have the composed function's expression as we had it here. We created it. Perhaps you don't want to create the composed functions, that composition function's expression. Could you still evaluate that composition function at some value? And the answer is yes, you could. If you first of all evaluated the interior function, we'll call it, evaluated that function, took that value, used it as the domain value in the exterior function, you would have then the resulting value for the composition function. So you do the interior function first. -1 mapped to 4. Take that value, put it in place of the x in the exterior function, the f function in this case. Evaluate that, and you'd have the same answer if you took -1 and evaluated it with your composition function. So that enables us sometimes to find the value of a composition function without actually having to create the composition function. Perhaps we look at that and say, you know, that could be a relatively complex function to compose. Perhaps I can just find the values by dealing with the separate functions. And we'll look at several examples of that in the next video.